Okay, number one, to start off with an easy question on this. So we know that F is equal to kV, and we want to find unit of K. So we know that F is equal to MA, therefore kg, ms to the minus 2 is the unit for that. And we know that the units for velocity are ms to the minus 1. Okay, so the m's cancel, and the s to the minus 1 goes up top, so that becomes s to the minus 1, so the answer is D, kg s to the minus 1. Okay, so let's look at number 2. We have this curved acceleration time graph. We know that the derivative of a velocity time graph is equal to the acceleration time. Therefore, if we look at the derivatives of these four graphs, we should be able to establish which is the correct answer. Number A, the velocity at t is equal to 0 is this horizontal line here. And as we see, as t increases, the gradient increases positively. So this corresponds to our first half of the graph here. Positive A, positive gradient here. After the velocity time graph intersects the horizontal line, then we move into this part of the graph. Here, you can see that the velocity is still positive, but now it is decreasing, and this corresponds to our second part of the graph here. It's positive but decreasing. So this corresponds to this part of the graph here. We can eliminate B and D because they are diagonal lines and they don't correspond to the curved lines here because their gradient is a horizontal line. The gradient should look like this for acceleration, or like this on this graph, so we eliminate these two. And it's not C because the gradient is actually negative here. We have negative gradient here, and this doesn't correspond to our positive A in the graph. So therefore, the answer is A. Okay, number 3. A projectile moving in air has a path shown, and we want to find direction of the net force at the point shown. Okay, so let's do a free body diagram. So if this is our point here with the projectile, then the mass goes down like this, and the resistive forces go in this direction here. So if we slide the mass vector, say mg, across to the end of the resistance vector here, we get this set up here. So then the net force must act in this direction here. So the answer is B. Okay, number 4. We have these two blocks, M and M, and we want to find the force that the block of mass M is exerting on the block of mass little m. Okay, so you have this force F here, so this must be transferred across from little m into big M by Newton's third law of motion. So we get force F here, and this must be equal and opposite to the force acting on little m, so we get this. Therefore, this is F here, this is F as well. So if we use F is equal to MA now for the big block, then the answer is just F on the big block is equal to MA, and by equal and opposite forces, the force that the block of mass M is exerting on the block of mass little m must be MA. So the answer is B. Okay, so number 5. This is a very common question in the world of physics and mechanics. It's about a block sliding down a plane. We're given the usual data, theta, mu naught, and n. And we have to find theta in terms of one of these options. So let's look at the block. It's mass m. So let's say this is mass m here. So let's make it into mg for the weight. And then of course we have the normal reaction here, which is n, like this. So let's see if we can bring theta into this diagram. So if this is theta down on the right hand side, this angle must be theta as well. So mg sine theta then, mg sine theta. So this is this force here acting parallel to the plane. This must be equal to the friction force. But we know friction is equal to mu times normal reaction, so mg sine theta is equal to mu naught n. Therefore, we can say the sine of theta mu naught n divided by mg. And then the next bit's easy, so the sine of theta is just the inverse sine of this, which is mu naught n all over mg. So the answer for this one is D. Okay, so this one is about an object falls from rest in a vacuum, and R is the rate of the change of kinetic energy with time t, and we have to find out how does R vary with time t. So the rate of change of kinetic energy, so this is the d by dt of the kinetic energy, and this of course is the d by dt of half mv squared. Now hopefully we all know that the rate of change of kinetic energy is equal to the power, okay? So this is equal to the power in the system, and we all know, I hope, that the power is equal to the attractive force times the velocity. So here the accelerating force is g, so that's constant, and the velocity is changing with time. Therefore, the answer must be A, straight line going from 0 up to some time t. So the answer is A. We could have eliminated C and D immediately because by common sense we know the power must be increasing with time. The rate of change of kinetic energy must be increasing with time, therefore it can't be C or D. And because power is directly proportional to velocity, the answer was A, the diagonal straight line, not B, the curved straight line. Alright, number 7. X has a mass that's twice the mass of Y, and the kinetic energy of X is 4 times that of Y, and we have to find the ratio of the two momenta here, X and Y. So we're given then that 4 times the kinetic energy of x is equal to the kinetic energy of y. Alright, so then that means that we can say 4 times a half mx v x squared is equal to a half my v squared y. Okay, so the halves will cancel on either side. We're also told that x has a mass that's twice the mass of y. So we can put that into our equation as well. So we can say then that 4 times 2m v squared x is equal to m times v squared y. So our m's will cancel here. So then we get 8 is equal to v y squared all over v x squared. So then we can say that the square root of 8 is equal to v y all over vx. So then the square root of 8, that's equal to 2 root 2. So the answer is going to be C, 2 root 2. Number 8. The energy is supplied at a constant rate to a fixed mass of a substance. The graph shows the variation in the temperature of the substance with time. So we have to choose which option is correct. So this is one of these questions that you just have to know about. There's no calculation in it. The intermolecular forces between the liquid molecules are greater than the intermolecular forces of solids. So more energy is needed to break the intermolecular attraction of the liquid molecules. Thus, the latent heat of evaporation of a substance is always greater than its latent heat of fusion. Okay, that's by definition. Therefore, the answer to this question is A. Number 9. For a fixed mass of an ideal gas, the pressure is proportional to which option? Okay, so we know that PV is equal to nRT, and we want to find pressure is proportional to what? So we can say P is equal to nRT all over V. So we know immediately that pressure is proportional to absolute temperature. By definition, in this formula we have to use absolute temperature, so it's not going to be A, it's going to be B, C, or D. Alright, so is it proportional to volume? Well, no, it's inversely proportional to volume, but we know that density is equal to the mass over the volume. Therefore, volume is equal to mass divided by density. So you can write P is equal to nRT all over mass divided by density. Of course, the density now goes upstairs into the numerator, so nRT all over m times d. So the pressure then is directly proportional to both the temperature, absolute temperature, and the density. Therefore, the answer is B. Okay, number 11, this wave traveling on a string question. So we've got two graphs, one for distance, one for time. So I hope everybody knows that velocity is equal to distance divided by time, or in this case we say speed. So speed is equal to distance divided by time. And we go up to our graphs here. We can see that the first graph gives us a distance of 5 here, and this corresponds to a time of 2.5 down on the second graph. So we just have to say 5 divided by 2.5 is equal to 2. Therefore the answer for this question is 2. Alright, so this question requires some careful reading to get the answer. So you have this unpolarized light of intensity I0, and it's incident on a polarizer with a vertical axis of polarization. The transmitted intensity of this polarizer is I. The light is then incident on the second polarizer with a vertical axis of polarization. The transmitted intensity of this polarizer is I2, both are I1 and I2. Well, when the unpolarized light passes through the first polarizer, it will have its intensity cut in half, because only the vertical part of the unpolarized light will be allowed to go through. Now when it passes through the second polarizer, the light has already been polarized, so the vertical polarized light will go straight through this second polarizer without its intensity being reduced. So the so the I2 intensity will also be I0 over 2. So the answer is B. Alright, number 13. Wave is traveling from medium 1 to medium 2. We have to compare the refractive indices and the wavelengths. So I think the best way to do this one is to imagine that medium 1 is air and medium 2 is glass. So this corresponds quite well to diagrams that we've seen for refraction of waves in our textbooks. If it goes from air to glass, the wave is always refracted towards the perpendicular. So we know that the refractive indice for air is less than the refractive index for glass. Therefore N2 here, N2 must be bigger than N1. Therefore we know the answer is going to be C or D. And for wavelengths, we also know that the wavelength, when it travels from air into glass, the wavelength is decreased. Therefore, the answer must be C. N1 is less than N2 and lambda 1 is bigger than lambda 2. Number 14. So the first harmonic of a standing wave is established in a tube with one end open and one end closed. When the length of the tube is increased by 0.1 of a meter, the next harmonic is formed. What's the wavelength of the sound? Let's draw a diagram here. So you've got a tube, one end open, one end closed. So the first harmonic will look something like this. This is lambda over 4. So this is L, length of the tube. Then L is equal to lambda over 4. So the length of the tube is increased by 0.1 of a meter. So we have to find the next harmonic formed. So if this was the first harmonic, the next harmonic will look something like this. So this is of course 3 lambda over 4. And now L is increased by 0.1 of a meter. So we can say L plus 0.1 is equal to 3 lambda over 4. But we know L is lambda over 4. Therefore we can say lambda over 4 plus 0.1 is equal to 3 lambda over 4. Therefore 0.1 is equal to 2 lambda over 4, or lambda over 2. Therefore lambda is equal to 0.2. The answer for number 14 is C. Number 14. So the first harmonic of a standing wave is established in a tube with one end open and one end closed. When the length of the tube is increased by 0.1 of a meter, the next harmonic is formed. What's the wavelength of the sound? Let's draw a diagram here. So you've got a tube, one end open, one end closed. So the first harmonic will look something like this. This is lambda over 4. So this is L, length of the tube. Then L is equal to lambda over 4. So the length of the tube is increased by 0.1 of a meter. So we have to find the next harmonic formed. So if this was the first harmonic, the next harmonic will look something like this. So this is of course 3 lambda over 4. And now L is increased by 0.1 of a meter. So we can say L plus 0.1 is equal to 3 lambda over 4. But we know L is lambda over 4. Therefore we can say lambda over 4 plus 0.1 is equal to 3 lambda over 4. Therefore 0.1 is equal to 2 lambda over 4, or lambda over 2. Therefore lambda is equal to 0.2. The answer for number 14 is C. Number 15, you have these 2 point charges, 4Q and minus Q. Fixed distance apart. What's the electric field? Where is the electric field strength equal to 0? Okay, so we know the electric field strength, say E, is proportional to Q over R squared. So let's say that these distances here are 1, 1, and this one is 2. So if we start at 4Q plus 4Q, the charge is 4, and if we go out to D, the distance is 1 plus 1 plus 2 is 4, so it's going to be 16. So according to this, then the field strength is going to be a quarter. So if we start then at minus Q and we go out towards D, then we have just Q by itself, so that's 1, divided by 2 2s are 4, that's equal to quarter as well. So this is minus quarter, this is plus a quarter, so the field strength is equal to 0 at D. Okay, number 16, a cylinder of copper with diameter D and length L has resistance R. What's the resistance of a copper cylinder with diameter 2D and length 2L? So we all know the formula for resistance and resistivity is R. R is equal to rho L all over A. So we know A is equal to pi r squared. But if the diameter is given, then of course area is equal to pi d squared all over 4. So let's look at the first equation. So that's R is equal to rho L all over A, or R is equal to rho L all over pi d squared times 4. And in the second equation, R is equal to rho times 2L times 4. And now diameter is 2D, so that's going to be all over pi times 4d squared. So the 2 4's cancel, and the we can get rid of the rho and the pi and the rho and the pi here because they're all constants. So then we can say that say this is R1, this is R2, so R1 all over R2 is equal to 4 divided by, get rid of the L's as well there, okay, number 17. The path of 3 particles with identical magnitude of charge but different mass is shown. And we have to compare the masses and the signs of the charges. So regarding the masses, I think common sense tells us the particle X must be a heavier particle because it follows a line of greater curvature. The lighter particles follow a line of less curvature. Therefore, we're looking at A or B as our initial guesses at the answer. To find the sign of the charge, we need to use Fleming's left-hand rule. And we need to be careful if it's an electron coming in, we need to reverse the direction using when we're using our fingers. So let's imagine here that the particle coming in here is an electron, like this. Then when we're using Fleming's left-hand rule, we have to go in the opposite direction like this. So using Fleming's left-hand rule, the second finger is the current, which must go in the opposite direction here. The magnetic field is going into the page, therefore the force is going down the ways, therefore the sign of the charge must be negative. So the answer is B. Number 18. The mass of planet X is 300 times larger than the mass of the Earth, and its radius is 10 times larger than the radius of the Earth. What's the gravitational field strength on the surface of planet X in terms of the gravitational field strength G on the surface of Earth? So I think we all know these basic equations here, that the weight mg is equal to g m all over r squared. The m's cancel here, so we get g is equal to g m all over r squared. So we know from the question that mx, the mass of x, is 300 times the mass of the Earth. Therefore we can say mx all over me is equal to 300. And we also know that rx, the radius of x, is 10 times the radius of the Earth. So if we use this information in our equations, so we know that gx is equal to g mx all over r x squared r x squared, and the g of e is equal to g me all over r y squared. So if we divide the two of these, the g's cancel, and we get gx all over ge is equal to mx all over me times r y squared all over r x squared. So this is equal to 300 times 1 over 100. Of course this goes as 3. So gx is equal to 3 GE. So the answer is C, 3G. Okay, so number 19. You have this artificial element seaborgium, and you have to find out how many atoms remain after 1 minute with half-life 15 seconds. Okay, so after 15 seconds, you divide by 2. Then after 30 seconds, you divide by 2 again. After 45 seconds, you divide by 2 again. And then after 60 seconds, you divide by 2 again. So this is the calculation, and if you do it, you should get 19A. Number 20, you have this pi meson particle, and you're given the equation. So you need to have a fairly detailed knowledge of subatomic physics for this one. You certainly can't guess it. So if it's a pi meson particle, you must know that the exchange particle is going to be a weak plus particle or a weak plus particle here. So that means the answers can be either A or C. So what is particle X? Well, again, you must know if it's pi meson decay, then it is a muon. So the answer is this. The answer is A. Okay. Which of the following is not considered to be a greenhouse gas? Well, the answer, of course, is oxygen. This is actually quite good for us. It doesn't destroy the atmosphere. So the answer is C. Number 22. This is about a black body, T, which has temperature T and peak wavelength lambda. Okay, so you must know that this is a Wien's law question, and for Wien's law, the wavelength of the black body radiation is inversely proportional to the temperature. So what's the peak wavelength if the temperature increases by 33%? So if it increases by 33%, then this means that we're going to have 1 over 1.33 times T. This, of course, is equal to 3/4. So the answer is B. Okay, so next one, simple harmonic oscillations, total energy E. What's the kinetic energy of the particle when the displacement from the equilibrium position is x naught over 2? So we need to know our kinetic energy formula here, which of course is half m omega squared a squared minus x squared. Okay, so we just have to look at a squared and x squared. So if we say a is 1, is 1 squared minus x naught over 2, so that's going to be x over 4. X naught squared over 4. So this gives us 3/4. So 3/4 E. So the new energy must be 3E over 4, which is 23C. Interference intensity pattern is obtained in an experiment with 4 slits. Okay, so number 25, you have a diffraction grating with 6,000 slits, and it's used to resolve 2 spectral lines, and you're given that information, and you have to find the minimum order at which the diffraction grating can resolve these 2 lines. Okay, so let's start off with our formula. Sine of theta is equal to n lambda all over d. So we're given lambda, so lambda is 500 by 10 to the minus 9, and you've got 6,000 slits, therefore d must be 1 over 6,000. So if you put that in your calculator, you should get n times 0.03. So what's the minimum order at which the diffraction grating can resolve 2 lines? So the difference for the first one is 0.05. So if we multiply 2 here by 0.03, that means we're going to get 0.06. So that means that the second order will be resolved. So the answer is B. Number 27, you have an isolated point charge Q located at point X, and you're given YZ is equal to 2XY. So this is 1, then this must be 2. So electric field at Y, well, we know that the field strength is 1 over R squared. So the electric field at Y must be 1 over 1, is equal to 1. And at Z, that's going to be 1 over 3 squared is equal to 9. 1 over 9. Therefore, it's going to be 1 divided by 1 over 9. That's equal to 9. So the answer is D. Okay, next then, you've got these long parallel plates, X and Y, have equal and opposite charges. The potential in X is Vx, and that in Y is Vy, where Vx is bigger than Vy. So a point particle, positive charge Q and mass m, is held at rest midway between the plates. So we've got plus Q here. So if Vx is bigger than Vy, then the direction of the field strength must be in this direction. So the charge must be moving towards plate Y, so the answer is going to be either C or D. And the kinetic energy, that's equal to the work done. So that's going to be equal to the difference between the two voltages, Vx and Vy, times Q. So the answer then is going to be D, because the particle is halfway between the two plates, so you have to divide the work done by 2, so the answer is D. Okay, number 29. You've got this hollow metallic sphere. Radius R has a positive charge Q. P is a point of distance R2 from the center of the sphere. So what are the electric potential and electric fields at point P? So you have to know that inside the sphere the electric field is always 0. So that means the answer is going to be either B or D. And the electric potential, well, that's always KQ over R, so it must be D. So the answer is D. Number 30. So we got the number 30. So you have a satellite of mass m in orbit around a planet of radius r and mass m. The total energy is given as minus g m over 4r. So what's the radius of the orbit? So we need to know then that the total energy formula normally is equal to a half g m all over r. So if we compare it to the formula given, we can see very easily that 4r is equal to 2r. Therefore, little r here is equal to 4 times big R all over 2. So little r must be equal to big R. So the answer is C. Number 31. In a direct current circuit, a current of 4 amps dissipates power P in a resistor. In an alternating current circuit, the average power dissipated in the same resistor is also P. What's the value of the root mean square current in the AC circuit? So this is more of a language question than anything else. If the average power dissipated in the same resistor is also P, then the average current must be the same. Therefore, the current is 4 amps because the root mean square current in the AC circuit is the average current. So the answer is 4 amps. C. Number 32. This is a Faraday's law, Lenz's law question. So you have this conducting ring and it's dropped from rest from above the ground and it falls through this uniform horizontal magnetic field, and you have to compare the acceleration going in and out. So when the ring enters the field, according to Faraday's law, it must have an induced magnetic field, and according to Lenz's law, this field must act in a direction that opposes the magnetic field causing it. Therefore, the ring will decelerate as it enters the field. So the answer must be C or D to begin with. When it leaves the field, it is still being restricted by the magnetic field opposing its movement. Therefore, the answer is D. Both of them are A is less than G. So the answer is D. Number 33, this is one of the easier ones. Which of the following parallel plate capacitors has the greatest capacitance? Well, if you've seen a parallel plate capacitor in the laboratory, it always has a large cross-sectional area and a fairly small separation. So according to that, the answer must be A. But from a more scientific point of view, you know capacitance is equal to epsilon A over D. So you have a big A and a little d, then this will maximize the capacitance. Therefore, of course, the answer is A. Number 34. A fully charged capacitor is connected to a 90 voltmeter. The capacitor is initially separated by air. Paper is inserted between the plates of the capacitor. What's the change in the charge on the capacitor plates and the change in the potential difference across the capacitor plates? So, the capacitor is fully charged, therefore we can eliminate C and D immediately. The charge won't increase. So we have to look at the potential difference. What's going to happen with that? Well, we know V is equal to Q over C. We also know that C is equal to epsilon A over D. So if the paper has been inserted between the plates, this means that the dielectric is going to increase, therefore the capacitance is going to increase. So if capacitance is increased, therefore the voltage is decreased, therefore the answer must be B. Stays the same and decreases. Okay, number 35. This is one of the more tricky questions, I think, on the paper. So you have a fully charged capacitor and it discharges through a resistor. The time constant of the circuit is tau. The initial energy in the capacitor is E. What's the energy stored in the capacitor at time t is equal to tau? So first of all, we need to know the discharge equation for the voltage. This is Vt is equal to V naught E to the minus T all over tau. Alright, so we're told that T is equal to tau, so we know then that at time tau this is going to be V naught E, so it's going to be minus T over tau, this is minus 1, so it's going to be equal to V naught all over E. Now we also know that the energy stored in the capacitor is equal to a half QV. So the time T is equal to tau for the voltage is V naught all over E. We can use exactly the same idea for Q. Instead of Vt is equal to V naught, we can have Qt is equal to Q naught. So that means that we have Q naught here over E. So you can see then the energy is going to be equal to a half times Q naught V naught all over E. So this is equal to D E all over E squared. Alright, number 36. So you have light falls on a metallic surface whose threshold frequency is F naught. The number of photons incident per second is constant. Which graph correctly shows how the current I emitted from the surface depends on the frequency F of the incident light? Okay, so hopefully we all know that F naught is the threshold frequency, which means below this no current can flow. Therefore, we can get rid of C and D immediately. So the answer is, does the current remain constant after we hit the threshold frequency, or does it increase? Well, it says in the question, number of photons incident per second is constant. Therefore, once we hit the threshold frequency, we're going to get a constant current. So the answer must be A. The current doesn't increase with time, so it can't be B. The answer is A. And then number 37, the Bohr model for the hydrogen atom in the Bohr model for the hydrogen atom, what is the angular momentum of the first excited state over the angular momentum of the ground state? Okay, so the ground state is n is equal to 1. It's not n is equal to 0. And the first excited state is n is equal to 2. So if you look in your data booklet, you will see that MVR, the angular momentum, is equal to NH all over 2 pi. So we'll let the angular momentum give it this symbol omega. So for n is equal to 2, we're going to get 2, and for n is equal to 1, we get 1. H and 2 pi are constants, so we don't have to worry about those. So this is actually quite an easy question. The answer is 2, C.